This is the 6-2 notes for Precalculus 2. In the previous lesson, you learned about several patterns that allowed us to use the law of sines to find missing angles and sides in an oblique triangle. So what were those patterns? The two primary ones we covered were ASA and SAA. If we could mark those patterns in an oblique triangle, we could use the law of sines. I also mentioned that this is another pattern that is possible. We just don't cover it. We're not going to cover it this semester because it's a little bit more complex. So if you go through the many arrangements of figures in terms of sides and angles, there are actually two more scenarios that could develop of importance, and they are as follows: side, 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 and side, angle, side. So what does that mean exactly? So a side, side, side scenario would represent you given all three sides of the triangle, but no angles in that oblique triangle. Okay, so that's one pattern. Another one would be two sides and the angle between them. So for example, we got two sides and the angle nestled between them, right? So these are the two other patterns that we're going to be dealing with in this class, but there's a very important note here that you might try to attempt to use the law of sines to figure out what these missing pieces are. So I'm going to prove to you that you absolutely cannot do that. So for example, looking at our side, side, side scenario over here, suppose that I decided to set up the law of sines with this triangle. So we would have 8 over the sine of the angle opposite, which is right here. We would have that equal to, let's do B, so B would be here, 10 over the angle opposite, 10 over sine B, which would also be equal to 15 over the sine of C. So if we did that, we would essentially get this little formula at the bottom here for the law of sines. Now here's the issue. If we took any two pieces of this at a time, like we've been doing in the previous section, let's say that, we normally have one missing variable, which allows us to use algebra to solve it. If you look at any two selections of these three ratios, they will always have two missing variables. No matter any two that we take, there will be two missing variables. So that's a problem because that means algebra is out the window. We can't solve one equation with two missing variables. That's not possible. So what does that mean? That means you cannot use the law of sines whenever you have a side, side, side pattern. So we're going to need an alternative. And by the title of the section, Law of Cosines, you will get that in a second. But let's just prove to you the same thing occurs with side, angle, side. So again, we're going to take A over the angle opposite. Okay, so A over the sine of 50. We got that. That is right here. Then we're going to say, okay, let's go to B. So B is 20 over the sine of B, capital B, which is here. And then 25 over the sine of C. Okay, so we have that down here, right? So we look at this and go, well, this is a little different. We do have an angle sitting there, but again, let's try taking any two at a time. So let's say we took these two. What do we have? We have a missing little a and a missing angle B. So that's not going to work. If we take these two, it's going to be just like the law of cosines applied to side, side, side. There's two missing angles. What if we took the first and the last? Again, we have a missing A and a missing big C. So no matter what we do in this scenario, we again cannot create an equation with one missing variable. Therefore, again, the law of sines cannot be used for side, angle, side. Okay, so what's the alternative? Well, again, we have what's called the law of cosines. Now, the law of cosines is a little bit more complicated equation. We'll talk about it in a second, but the key is if you see any triangles with a pattern of side, 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 or side, angle, side, you are able to use the law of cosines. So what do these formulas look like? Okay, yes, they are pretty crazy. For example, our first one is a squared equals b squared plus c squared minus 2bc cosine a. Mouthful. But the general concept here is, if you look at the last equation at least, you'll kind of see that you got the Pythagorean theorem here at the beginning of it, and then you're going to have to subtract minus 2ab cosine c. A lot of students in the beginning often say, well, does that mean we have to know 3 different formulas? Not really. In reality, these are all the same formula. You just always have to understand that you're going to have one side squared on the one side, and then the opposite angle will always be related to it at the end of the problem with a cosine. But then whatever you square on this side will be the same variables that are here. So if you look at the problem, b squared match with b, and then the 2 squared variables repeat over here. So the key is that it is kind of all the same formula, but and you'll see in a second why they put the 3 different ones. But the reason why I say this also is that the sides are not always going to be a's and b's and c's. Sometimes it's going to be x, y, z. Sometimes it's going to be a whole different bunch of letters. So you don't want to get hooked into the formula with the ABCs. You want to understand what the formula actually does for this scenario. So there is a couple things of importance here that you want to make sure that you realize. So I'm going to read this here. It says, another important fact is that you will never use the law of cosines more than once in a problem. Okay, that is very important. You'll never use the law of cosines more than once in a problem. So why is this? Because once you use it one time to get one of the missing pieces, you will then be able to use the law of sines thereafter to find the rest. Now, I gotta tell you, if you have a choice to using this crazy formula, or I think most of you had a pretty, I'm assuming, a pretty straightforward time using this formula, I think you're going to choose to use the law of sines over the law of cosines. Obviously, in the beginning of SSS or SAS problems, you must use this once. But after that, you can then default to law of sines and then have a much easier time when you're actually doing the computations. There is a little bit of a strategy to that, which we'll talk about in a second, though. Okay, let's start with using side angle side triangles and its application with law of cosines. So these gray boxes that you see, that you're going to see for these 2 triangle patterns, are a little bit more important than a typical gray box where you basically have a strategy and you learn how to do the problem and you abandon even looking at the gray boxes. Now there's a little bit more involved here that I'm going to cover as I do the problem, so I'll point it out as we go. There's no sense in actually listing them out now, but I'll show you. So let's do, in our first problem here, we're going to solve the triangle ABC. So here's your triangle over here, ABC. It looks like we have to look at this pattern here. Remember, solve a triangle means find all the remaining pieces. So if you look at the pattern that we have, we're given the side 5, the side 7, and we're given the angle between the 2 sides. So if you're looking at the scenario, clearly this is going to be a side angle side pattern. Okay, once we know that it's a side angle side pattern, then we're going to be following this strategy using step 1, the law of cosines. So in step 1, we need to use the law of cosines to find the side opposite the given angle. So we have to find A. That is our goal. So what does that look like? So we'll say step 1, Roman numeral 1. So whatever we need to find will be the variable squared that is on the side by itself. So that means we're going to start with a squared on the left. So if we go back to the formulas, technically we're going to be using this one, but I'm going to try to get you away from that in the second problem. But for now, we're going to concentrate on that. So what does that look like? we always square the sum of the other two sides here, and then we subtract 2 times the same two variables, b and c, times the cosine of the angle opposite the side on the other side. Okay, so that is the strategy always for the formula when it comes to law of cosine. So again, we're looking at the side opposite the given angle will be squared on the left side of the equation, right? Then the remaining sides will be squared here, minus 2 times the same two sides not squared. Then you're multiplying that times the cosine of the angle that's opposite the side. That will be the strategy that we're going to use for all of the problems, instead of trying to memorize the formula. So how do we apply that? So let's just start subbing in values. So a squared, obviously we need to find. If you look, this is angle B, so that means this is side B, which means this is side C for our problem. So it's going to be 5 squared plus 7 squared minus 2 times 5 times 7 times the cosine of the angle opposite A, which is 49 degrees. All right, so we have a very big formula here that we have to basically compute, but realize there is a lot of issues here that students have when it comes to order of operations. So what I usually do is I usually have students compute this first. So it's going to be 25 plus 49 minus 2 times 5 times 7 is 70. Cosine of 49 degrees. Don't calculate cosine of 49 yet. So we have to be careful of order of operations here. Basically, what I get is, and I just trying to prevent this, is students will literally take this, do the math, and then multiply by cosine of 49. That is illegal. You cannot do that in the setting. Why? Because there's an order of operations here where we have to do the multiplication first before we start combining it with the 25 and 49. So what I usually do is I do it this way. So first, let's add these together and get 74 minus 70 cosine of 49. Then literally in the calculator, you're going to find 74 minus the product of these two. Do not, so for example, do not in the calculator, hold on, in the calculator, this is a no-no, so don't do this and just leave it like that. If you do that, the calculator does not know PEMDAS, so it's going to do this first and then multiply that by this. That is, again, illegal. What do you need to do instead? You need to do this when you're putting it in the calculator. So 74 minus 70 times, little dot, cosine of 49 with parentheses. So just a little bit of a tip there for you. So what you want to do basically is just like, make sure your calculator is in degrees, right, as normal. So you just want to type it into the calculator, 74 minus 70 times the cosine of 49 with the proper parentheses, and you are going to get that a squared is equal to 28.075, let's say 9. Okay? So once you get that, then you know that you have a squared setting up here, which means you have to take the square root of both sides and get a is equal to plus or minus 5.2987, and this is an approximation, so we're going to change the sign. But we obviously know that we don't need a negative sign because we can have a negative value, but that means essentially that 5.2987 is going to be the length of the side A. So note, if you want to be extremely accurate, you can actually do this instead. So you can do A is equal to the square root, technically plus or minus, of 74 minus 70 cosine 49 in your calculator. So you could actually do this entire thing, making sure there's parentheses here, as one calculation and get the most accurate answer humanly possible. I'm not going to hold you to doing exactly that. If you want to do it the way I just did, I'm fine with that. But worth noting, you can get exactly the most accurate approximation you possibly can by doing so. But in the end, we are going to be looking for decimal sides, which is, I know, not common in this class, but we treat these as application problems and we get the remaining pieces. So what's next? So we go back to our steps that we were dealing with and go to step 2. This is important. It says, now use the law of sines to find the angle opposite the shorter of the two given sides. Okay, so this is a very big deal, because in reality, you could have used the law of sines to find C or B, but the key is that you need to choose the smallest of the two remaining sides, so we're going to pick 5 and find angle B. So step 2. Make sure you do this. If you do not use that strategy, you will end up with some wonky answers. Best way to put it. So I'm going to put 5.2987 over here, and then I'm going to get rid of some of the noise that I wrote in here so we can get a better look at the triangle. So how do we do this? Well, what are we given with the law of sines? The law of sines, we're always looking for an angle opposite a side. So the only angle opposite the side right now is 5.2987 over the sine of 49. So we need to set up a ratio in order to figure out this angle opposite the side, the smallest of the remaining sides. That is 5. That is not a 5. Hello. That is a 5 opposite the sine of B. Okay, so you guys know how to set this up. It's just it's going to be a little different than what you are used to. Okay, so remember, we can do cross multiplication, so we can get 5.2987 times the sine of B is equal to 5 times the sine of 49. We then can divide by 5.2987 to get 5 times the sine of 49 over 5.2987. So this reaches a point where you should be very familiar with how to find B. The only way to get the angle B is to use the inverse sine function. So this is equivalent to B equals the sine inverse of this entire quantity, 5 sine 49 over 5.2987. So you would type this into the calculator as is, and you will be able to find the missing angle of 45.4 degrees. Okay, take note that I did round this answer to 1 decimal. That's usually what I'm looking for in a problem, but hopefully you realize why I didn't round to 1 decimal here, because I actually had to use this in my problem, and I did not want to have a huge rounding error. So in the beginning, when you're finding the missing pieces using law of cosines, I usually round to 4 decimal places, but then when you get to find the angles, the missing angles, I stick to 1 decimal place because it really doesn't matter too much after that, but that is the strategy, at least for that. Now, what about the remaining side? It says, find the third angle by subtracting the measure of the given angle and the angle found from 180. Okay, so this should be very easy for you. So let's say we're going to step 3. So we currently have this angle as 45.4 degrees. So therefore we have 2 angles, and if we have 2 angles, we should be able to find the remaining angle. How do we do that? We do 180 minus the sum of 49 and 45.4 degrees, and we are going to get 85.6 degrees as the remaining angle C. So if you look at all of the setup, we were given 3 pieces of the oblique triangle, and we had angles that were remaining. Now, the last thing I want to do here, just to be clear on how this is set up, is I'm going to get rid of all the pieces here that I have, and then I'm going to put the remaining angle here, 85.6. Now again, recall from my Law of Sines lesson what we talked about. The size of the sides is in the same ratio as the size of the angles in terms of size. So if you look at, for example, the biggest side of this figure is 7, which means the biggest angle is opposite it. If you look at the second biggest side, it is A. The second biggest angle should be opposite it. And the smallest side should have the smallest angle opposite it. Why do I say that? Because when you are done with the problem and you actually get your answers, you will probably not be too shocked to find out that many times I get answers that don't make any sense whatsoever when it comes to setting this entire figure up so that the size and the angles are in the same proportion. Please be careful with that. Always when you're done, write them on your figure. Make sure that the biggest side's opposite the biggest angle, medium side, medium angle, smallest side, smallest angle, so that you're essentially checking your work. Okay, so let's do another example using the law of cosines. Just because there's so many steps and there is a strategy, and sometimes you're not given the variables that you like. So students love ABCs, but because they fit the formulas quite nice up here. But what if you weren't given that and you had to figure this out? So I think this is a very valuable strategy in order to follow. So first things first, the pattern. We have an oblique triangle over here on the right because there's no right angle. So what's the pattern? We have two sides given, and then the angle between them. So if that is the case, we have an A nestled between two S's. So that is a side angle side scenario. So if we have a side angle side scenario, then we can clearly look at using the law of cosines and then the law of sines in order to find the missing pieces of the figure. So let's go through the steps again. Let's go. Step 1. We need to use the law of cosines to find the side opposite the angle that is given. Angle given, side opposite it. So here's the strategy. So you don't need to look back and try to figure out A, B's, and C's here. You just have to follow, as I'm speaking here, what the strategy. You always take the side that you're trying to find on one side and square it. On the other side, you take the other two sides. So let's throw the variables in here. So this is P and this is Q, right? So we're going to take the sum of the two sides, each squared. We're going to subtract 2 times the sides not squared times the cosine of the angle that is given, which happens to be opposite R and shares the same type of letter, so R. If you follow that strategy in every problem, you won't have to worry about memorizing a formula to figure this out. So let's go ahead and work through the formula as we have been. So R squared is going to be equal to 6.9 squared plus 2.6 squared minus 2 times 6.9 times 2.6 times the cosine of our angle 117. Okay, so this is a lot messier. So if you do a little bit of math here, you're going to get the sum of these to be 54.37. Then you're going to get a product over here of 35.88 times the cosine of 117. Okay, if we take some shortcuts here, we basically can say that R is equal to technically plus or minus, but we know minus is thrown out, the square root of this entire value. Okay, but remember, in the calculator, make sure you put parentheses around these two values when you're plugging it in, or you're going to get the wrong answer. If you do this, you're going to get 8.4059. So remember, this is the side. Technically, we do 1 decimal place normally when we're doing these problems, but we know from the previous problem that we're going to have to use this value here in order to solve for the rest. So let's not create a lot of error. We'll go all the way to 4 decimal places. Okay, step 2. Remembering what we have to do here. We have to use, let me get rid of some of this stuff here. We have to use the law of sines to get the angle opposite the shorter of the 2 remaining sides. So if you look at the 2 remaining sides, the shorter one is 2.6. So we need to find Q. How do we do that? We need to first find an angle and a side opposite it that are provided. Well, we already did that. We generated that for R, for side R and angle R. So we're going to take the 8.4059 that we calculated and put it over the sine of 117 to find our important ratio, because this is the ratio that's going to set up for the rest of the sides and angles. So what do? We go to the Q's. So we get 2.6 over the sine of Q. We have set up. So again, cross multiplication, we're going to get 8.4059 times the sine of Q is equal to 2.6 times the sine of 117. We have to divide both sides by our decimal value, 8.4059, and we end up with a scenario where we must use sine inverse to find the missing piece. Okay, if we do so, we are going to get approximately 16.0 degrees as the angle Q. Okay, the remaining step, of course, is if we throw 16 degrees in here, we have an angle P that we can find using 180 minus the sum of 117 and 16, which is going to give us 47 degrees as the missing angle P. So P is equal to 47 degrees. Okay, so we found the missing remaining sines using the same strategy that does not change. Just remember a couple things. Remember, step 2 is the key step. That's the step where you must choose the smallest side of the remaining sides. If you don't, you will get a different answer based on some weird behavior that occurs in triangles. So make sure you do that. Another fine point, now that we've completed these 2 problems, another important sort of thought process here is students will often confuse sine and cosine in these formulas. So I will get a lot of students that will put sine here by mistake, or they will put cosine here by mistake. Be very, very careful not to do that, right? So I'm removing it as we go here. Don't do that. Because if you do that, all craziness will break loose, right? So make sure that in these scenarios you follow the steps and just the way they are, and make sure you're using the proper formulas. Okay, so what about side, side, side? So what if you were given an oblique triangle and all the sides were given, but none of the angles? Okay, what if that was your scenario? Well, it turns out that we can also use the law of cosines in order to determine the missing pieces of the triangle. So we're going to start with an ABC triangle, just so that we have the formulas down when we're doing this. But again, there is a part to the strategy that you must follow, or you will not get what you need out of the problem. So the key is, though, we again need to start with the law of cosines. So let's read. It says, use the law of cosines to find the angle opposite the longest side. Okay, here we go. So this is the important step in the side, side, side figure. Just like in side, angle, side, what was the important step? It was step 2 with the angle opposite the shorter the given sides. For side, 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 the important step is 1. So we find the angle opposite the longest side. So look at our triangle, 6, 7, 8. We need to find angle A. Okay, so how does this work? That means at the end of our problem, we are going to have cosine A. Okay, so what does that mean? That means that the side A, which is our circled side over here, is going to be the one that's squared on the other side. So let me write in the variables here, B and C. So filling in the blank, we do the sides, the remaining sides sum squared minus 2 times 6 times 7 times the cosine of A. So what's changed? Our missing variable is no longer here, it is here. Okay, so remember, going back, let's go back to our first problem. Where was the missing variable? It was here, and we had an angle. So now it's going to be the opposite. So now we're going to have no longer the missing over here, but instead the missing angle is over here. So that's going to obviously change a little bit with how we solve it, but that doesn't mean we don't, find the missing pieces the same way. So what do? We just solve. So over here this time we're going to get 64. Over here we're going to get 36 plus 49 minus 2 times 42, which is 84 cosine of A. Okay, so this time we need to isolate this piece over here, so be careful. Remember, this 84 is on cosine A by multiplication, which means we cannot separate this 84 from this right now. We first have to find this. 36 plus 49 is going to be, it looks like 15 and 1 is 85, right? So if we have 85 over here, that means we basically need to subtract 85 that way. So 64 minus 85 is negative 21, which is equal to negative 84 cosine A. Okay, be careful here. Some students forget to bring the A with them, or not the A, the negative with them when they go. So this right here is still negative, this 84. But again, we cannot in this problem subtract the 84, 85, and the 84 right here. Don't do that. Okay, students will do that and they'll get completely messed up to what you're doing. You cannot do that. You need to subtract the 85 from the 64 on the left and leave the negative 84 cosine A. So then we're going to divide both sides by negative 84 and get 0.25 on this side. Once we get that, then clearly we need the cosine inverse of 0.25 in order to find our missing angle A, which is going to be 75.5225 degrees. So again, notice 4 decimal places. Why? Because just like last time, we're going to need this missing piece in order to do more calculations. So instead of rounding to 1 decimal place, we round to 4, and we can actually throw that into our picture now in order to generate what we need. Okay, so if the next step, we need to use the law of sines to find either of the 2 remaining acute angles. So no strategy here. We don't even have to worry about that because it doesn't tell you bigger or smaller. So basically you can pick which one you want. Since we did A, I'm just going to choose B. So this is where I'm going next, angle B. So what do? We take the information we know of angle and side opposite it to form the first important part of our law of sines ratio. Okay, we set that equal to the B's. So our side B is 6, and we don't know the sine of our angle B. So again, cross multiply. So we're going to get 8 times the sine of angle B is equal to 6 times the sine of 75.5225. We divide both sides by 8. So we're going to get sine B is equal to 6 sine 75.5225 over 8. If we do so, B is going to be equal to the sine inverse of this piece, 6 sine 75.5225. Typo. Over 8, and when we do this calculation, we get approximately 46.6 degrees. Okay, so we have 2 of the angles now. So I'll throw that in there, 46.6 degrees. So again, the only thing remaining is to find the missing piece of it. So you're going to add 75.5225 and 46.6, which is going to give you approximately, for angle C, it's going to give you approximately 57.9 degrees as your missing angle. So when you're done, as I say, normally you can put your angle in there, let's say 57.9, and you can verify that you have the biggest side opposite the biggest angle, the medium side opposite the medium angle, and so forth, just to make sure that you don't have any mistakes in your work. I mean, technically you could have minor mistakes here or there, but usually major mistakes will result in proportions that are off kilter. Okay, let's just do another problem of Law of Cosines, side designation, just to make sure that all is good. Sometimes the work can be a little crazy. It's also great practice. Just whenever we do a second problem like this, it might be wise to possibly try to do it yourself. So for example, if you did number 3 and you're like, hey, this isn't so bad, then why not on a separate piece of paper try doing number 4 by yourself, and then let's see if we get the same thing. And truthfully, in class, that's exactly what I would have done. I would have done number 3 with you and then had you do 4 and then put it on the board for you to check. So feel free to do that. Do you have to do it? No, you can just get the notes, but maybe it might be worth it just to get a little bit of practice within the lesson. So again, where are we starting with? We need to use the law of cosines because we have a side designation for the pattern in our oblique triangle. So what does it say to do? So let's return to the strategy again, right? So let me just get this up. There it is. We need to use the law of cosines to find the angle opposite the longest side. Okay, so we found the longest side, which means we need to find this angle. So at the end of our problem is going to say cosine of y. But what do? So the side opposite it is always going to be the one squared by itself on the left side. So then what do? We take the other sides, x and z, and we square them. So 5.1 squared plus 3.5 squared, the sum of them. We do 2 minus those two values not squared times the cosine of our missing angle y. Okay, so that is how we set all of these up, and that's the strategy. So let's do some math work. So this is going to be 62.41. This is going to be 12.25. This is going to be 26.01. This is going to be 35.7 cosine of y. Okay, if you do a little bit of math here, 12.25 plus 26.01 is going to give you 38.26. All right. So for that 38.26, remember, you cannot combine these two values. Why? Because order of operations would make you do this multiplication first. And just to be clear, if I was doing something like 2 minus 5x is equal to 8, right? If you right now combine the 2 and the 5, you would probably laugh at me because you would know that you cannot do that algebraically. It's just that when you see something crazy like this, sometimes your brain goes in the wrong direction. So just realize we need to subtract 38.26 from both sides and get 24.15 is equal to negative 35.7 cosine of y. Remember to bring that negative with you. So if we divide, we're going to get cosine y is equal to negative 0.6765. Round the 4 decimal places to make sure that you're good. Now note, don't be scared that you're getting a negative sign on this side or a positive. It's just that scenario sometimes happens. Like in this problem, we get a positive 0.25 over there. Sometimes you will get a negative. It's just the way trig works. If you do the work, you're going to get y is equal to the cosine inverse of negative 0.6765 which means y is approximately, rounded to 4 decimal places, 132.5685 degrees. Okay, round to 4 decimal places, so we don't have to worry about rounding later. So if you go in the picture, you now know that this angle here is 132.5685 degrees. Okay, so if you recall, step 2 is not supremely important. They basically say find either one of the remaining angles that are left. So there's no size requirement here. So for example, I just picked Z, right? So could you have picked X? Sure, but I just picked Z, so that's what I'm going to do. So what do? You take the ratio of sines for law of sines to set up, which is 7.9 over the sine of 132.5685. Remember, don't get confused by sines and cosines here. That is your major law of sines ratio. So then you set that up with a ratio, let's say to find Z. So we know side Z is 3.5. We need angle Z, so sine of Z. We do a little bit of work here, so we're going to get 7.9 times the sine of Z is equal to 3.5 times the sine of 132.5685, right? So if you do a little work here and do a little shortcut, if you divide 7.9 over on the right and then do the sine inverse, we're going to get Z equals the sine inverse of 3.5 times the sine of 132.5685 over 7.9. Okay, so I just did a little bit of a skip step there since this process can be very intensive, so I just skipped a little bit of there. But you get Z is approximately 19.0 degrees. Okay, so that is here, 19.0, so what's to remain? Again, we just have to take this, do 180 minus the sum of 132.5685 plus 19. And if we do that and round to 1 decimal place, we're going to get 4x, approximately, I think it's going to be 28.4 degrees. Okay. So that is how you use the law of cosines in SAS and SSS situations. Say that a lot of times fast, but we're going to move on to application problems now. Okay, what is the most common application of the law of cosines? It is, ta-da, bearings. We're going back there again. So let's see some applications of this so that we can you can get some of the problems working on your homework. So it says 2 ships leave port at 4 p.m. All right, so we got a port here, right? So they're leaving at 4 p.m. It says one is headed at a bearing of northeast, so that looks like it's this one. So remember, we always measure bearings to the y-axis. So that's going to be north 38 degrees east as our bearing. It says it's traveling at 11.5 miles per hour. Okay, we'll get to that in a second. The other is traveling 13 miles per hour, again in a second, at a bearing of south 47 east. Okay, so it looks like that's this ship traveling in the southeast direction. Measured to the y-axis, the bearing is 47 degrees. Therefore, we basically have 2 ships that are moving in opposite directions. So we basically need to find, in this scenario, it says how far apart are the ships when the dinner is served at 6 p.m. Okay, so what is essentially our missing side? It is this one. So we need to find this at 6 p.m. if these ships have been doing this. It sounds like, train leave the station problem, basically, but it's actually quite similar. Okay, so how do we proceed? Well, if you look at this figure right now that we have, it's actually looking like an oblique triangle. Now, it could be a right triangle. We have to figure that out first. So we need to know this angle right here. How do we do that? Well, we know that on a line from here to here, there's 180 degrees. So if we need to find that angle, we do 180 minus the sum of 38 and 47. If we do that, we're going to get 95 degrees as the angle in the middle. So we indeed know that this is going to be oblique because this is actually obtuse, this triangle. So right now we have only one angle in the triangle. So what do we know that could help us with the sides? Clearly, the speed. Okay, so the first ship is traveling at 11.5 miles per hour. So think about this for a second. If it travels at 11.5 miles per hour, how many hours has it traveled? Well, if you look at the scenario, it's traveled for 2 hours when they're asking you to make the measurement, which means we should be able to find what the length of this side is by doing 2 times 11.5. So again, there's 11.5 per hour, so we need to find how many are per 2 hours. We multiply 2 times 11.5 and we get 23 miles for that side. We do the same thing for the other side. Let's probably do different colors here, right? So in this side, we do, this has again been 2 hours, but this one has traveled 13 miles per hour. So this is going to be 2 times 13, which is 26 miles traveled. So right now, what has happened is we have ended up with a picture that it looks, that's a terrible picture, hold on. We're ending up with a picture that looks like this. We have 23 over here, we have 95 over here, and we have 26 over here, and we need to find the missing side, x. If you look at this picture right now, this is a pattern of side, angle, side. Which means if we have a pattern of sine, angle, side, we should be able to use the law of cosines in order to find a missing piece in the beginning. So this is going to be a little different than the previous problems that we did, right? Because we're not trying to find all the sides, we only need to find this one. So if we return to our side, angle, side scenarios, the first step was always use the law of cosines to find the side opposite the given angle. Well, luckily enough, if we return to this problem, the side opposite the given angle is the side we need to know. So this is going to be a one-step problem in the beginning here. So how do we set this up? We always take the side opposite the given angle, square it, and we do this other side squared minus 2 times the product of the sides not squared, times the cosine, law of cosines, of the angle. So this is actually returning to our the different scenarios where we have the missing piece on this side. So all we have to do is solve this like we did before. So this is going to be x squared is equal to, the sum of these two sides is 1205. Squared, the sum of them squared is 1205, minus, this is going to be 1196 cosine of 95. So remember, you cannot put these two together. That is illegal. So if you want to do this all in one step, you can do x is equal to technically plus or minus, but we know it's not going to be minus. 1205 minus 1196 times cosine of 95. Use the parentheses on your calculator, and you will end up with 36.2 miles as the answer to the problem in terms of how far the ships are apart after they run these routes. Okay, let's try the last problem here. It says the distance on the map from the airport in Miami, Florida to the one in Nassau is 295 kilometers. Okay, due east. So we basically did a perfect east setup here, Miami to Nassau. So it says Bangor, Maine is northeast of both cities. True, northeast for both of them, right? Its airport is 350 kilometers from Miami, so this way from Miami, and 2,323 to Nassau, all right? What bearing would a plane need to fly from Nassau to Bangor? Okay, so we have to basically look at what bearing this is going to take. So the key is you have to just sort of stare at this little triangle over here. So what is our east-west line? It's right here. What's our northwest line? Right here, right? So if I want to go from this point to this point, right, what would be the bearing? It would be this little angle right here. Okay, so I'm going to get rid of all the picture for a second. So all of the markings that I did. So the missing angle in this problem is this little sliver right here. Okay, once we know that that's the missing angle, we should be able to proceed to figure out this problem. Why? If you look at this north-south line right here that we have, and you look at the fact that this is due east, that makes this angle a right angle, which means if I can find this entire angle right here, I should be able to subtract 90 to get my missing bearing angle over on the right. That is the strategy of this problem. It's understanding that if I can find the big angle in the oblique triangle that was provided, then I can subtract 90 to get that question mark. Now, why is this relatively straightforward? Because if I look at this triangle without anything in it, so I ignore the north-south line, this is an oblique triangle with how many sides given? All three. So what pattern is that? That's side, 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 which means we should be able to use the law of cosines to find any angle in the triangle. So let's start there. Okay, so one of the things that's important here is when we use the law of cosines with side, 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 we need to find the angle opposite the longest side first. We luck out here because the angle we need is actually opposite the longest side. So we're good to go. So what do? Again, this angle here, which we will call capital N, so we're going to do M, N, and B for the angles. The angle opposite that, capital N, is going to be cosine N at the end of the law of cosines problem. So this, which is little n, is going to go in the front, so squared. So 2,350 squared in the front. We're going to square the other two sides, no order of preference. We subtract 2 times the product of these two sides not squared, and we multiply by the cosine of the missing angle n. Okay, we do some work for this. When we square these, the sides are enormous, so stay with me. This is going to be 5,522,500. In other words, 5,522,500. If we take these other two here, we're going to get 87,025. We're going to get 5,396,329 minus 1,370,570 times the cosine of n. If we add these two together and subtract them this way, we're going to get 39,146 on the left, and we're going to be left with just the negative 1,370,570 cosine n on the right. Therefore, the only thing left to do is to divide both sides by the negative 1 million, so we're going to get negative 30 or positive 39,146 over negative 1,370,570. And in order to find n, we have to do the cosine inverse on this side of this crazy fraction of big numbers. Okay, if we do so, we're going to get approximately 91.6 degrees. Okay, now, there might be a tendency here for everybody to circle this as the right answer, but this is not the answer. This is, let me just erase the picture again. This is the entire angle from here to here, 91.6 degrees. The answer to the problem is this little sliver right here, this little bearing. So since, again, we know this is 90, then the sliver angle is going to be 91.6 minus 90, which is 1.6 degrees. Again, this is the angle, but not the answer, because all bearings have to be calculated with directions. So, if it says in this problem, it says fly from Nassau to Bangor, which means we're going in a northeast direction. So the answer to the problem is north 1.6 degrees east.